Welcome back everyone. In this lecture we will see various characterization of trees. So, let us begin with recalling what is a tree. A tree is a connected graph that has no cycle. Okay, so for example, if we take a path on n vertices, so that is indeed a tree. And then one can also look at what is called the star graph. So, graph of the form like this. So, this is let me call it as Sn. So, this is again a tree. So, we can give various examples that is I will leave it to you to construct more examples of trees. So, let us actually study some basic properties of trees, then along the way we will actually characterize them using some characterization that I stated in the last class. So, if you take a tree, okay, let us call T to be a tree, okay, and then T is given by the vertex set V and the edge set E. So, like I said before, a tree must be a simple graph because multiple edges will create immediately cycles. So, we do not want any cycles in a tree. So, in a tree if we take any two vertices, they must be connected by a unique path. So, that one important characterization of a tree. Okay. So, in a tree any two vertices are connected by a unique path. Okay, so, why this is true? By contradiction, let T be a tree and assume that there are two distinct UV paths, call it P1 P2 connecting U and V. So, you have U and then you have V and then you have like one path P1 and then another path P2 connecting this vertices U and V. So, now suppose P1 is different from P2. So, then what happens? There is an edge E of P1. So, that is not going to be an edge of P2. So, you assume that P1 is different from P2. So, that would imply immediately there is an edge E, let us call it xy. So, the xy is going to lie somewhere here. So, this is an edge. So, this is an edge in P1. So, that clearly not an edge in P2. So, not on edge in P2. Okay. So, the clearly what you can do, you can actually look at the graph P1 union P2 and then remove this edge. Okay. So, what you do, you just simply remove this edge from this path P1 union P2, and by diagram itself it is clear that it is supposed to be connected. Okay. So, since you have chosen this edge in P1 which is not an edge in P2. So, that means when you remove this edge from the union of these two paths, so the resulting path is going to be still connected. So, it therefore contains an path xy inside P, which is this P1 union P2 minus E. So, now if you take that path, so let me write it down. So, the diagram is little bit misleading because I have just drawn it like P1 and P2 are disjoint paths having only U and V actually having the common vertices. But anyway, the argument is clear. When P1 is different from P2, you can pick an edge xy in P1, not an edge in P2. So, then P1 union P2 minus E will be still connected. So, since this P1 union P2 minus E is still connected, you have a path, okay, xy path, let us call it P. So, that you have it in this P1 union P2 minus E, P1 union P2 minus E. But then what happens to this path P if you add this cycle this edge E? So, then this becomes a cycle, okay, and this actually contradicts the acyclic property of the graph G, okay, and this is a cycle inside T, that is a contradiction. So, basically you have these two paths, okay, and then this edge. So, now when you look at this P1 union P2, so that actually kind of the way I have drawn, it looks like a cycle, but the problem is you may need to actually choose properly a cycle, because the cycle that we have actually defined, that has this definition of being a trial and then having all the edges distinct and so on. So, one has to take care of that. For that purpose, what do? You choose an edge that is in P1, that not in P2. So, then look at the path that actually connects xy inside this P1 union P2 minus E, then you add that edge. So, then that will take care of the required cycle that we are interested in, okay. That is the technicality of the argument. So, that tells you that one cannot have two different paths between the given vertices u and v. So, that tells any two vertices are connected by a unique path in any tree. Okay, this proves that tree implies two vertices are connected by a unique path. So, now why the converse is true? Suppose two vertices are connected by a unique path in given graph G, then that graph must be actually a tree, because if it is not a tree, so then what will happen? It will have a cycle. So, the cycle will look something like this. So, then this vertex u and v will have two different ways to reach. Like what you can do, you can actually look at this edge, which is one path between u and v, and then you can also take this another path that actually goes around the cycle, and that is going to give another path between u and v. So, there are clearly two different paths in a cycle between any two vertices, then that tells clearly that your graph that you started with does not satisfy the hypothesis that you started with. So, that implies that you cannot have a cycle in given given that graph that satisfies the property that any two vertices are connected by a unique path. So, that implies that must be a tree. Okay, so, now we can actually tell something very strong about the number of edges that can appear in the tree. For example, let us do one example. So, let us take something very small and then count explicitly what happens to So, let us look at this tree. Okay, let us label 1, 2, 3, 4, 5, 6, 7. So, then now if we count the number of edges in this, you can see that it is exactly given by, so E1, E2, E3, E4, E5, E6, 6, which is exactly 7 minus 1, which is the number of vertices minus 1. And this is not something accidentally happened. So, this is always true in a tree. So, here is the theorem. If T is a tree, then the number of edges must be equal to the number of vertices minus 1. So, how one can prove this? One can prove using induction. So, induction on the number of vertices. Suppose this nu which is 1. So, then that would imply that our tree is just a graph with one vertex. So, that means epsilon is 0. So, we have 1 minus 1 which is 0. So, we are done. If nu is 2, then this has to be k2. So, then the epsilon is 1 which is 2 minus 1, in that case is also we are done. So, by induction we assume that the theorem is true for all trees on fewer than nu vertices, and let T be a tree on let us say nu vertices. So, what we can do? We can actually take an edge uv inside the edge of this tree. So, then we can actually look at this T minus uv. So, you just remove that edge. Okay. So, then this G minus uv contains no uv path. Okay. Since uv is the unique path between the vertices u and v. Okay. So, you have this vertices uv, and this uv is the unique path between that. Okay. So, if you remove it, since T is a tree, any two vertices will have unique path between them. So, because u and v are adjacent in E, and that edge is uv is the unique path between them. So, this G minus uv contains no uv path. So, it contains no u comma v path. So, that means this G minus uv is indeed disconnected. Okay. So, because once you remove this edge from the tree, okay, so since there is only one unique path between u and v, which is the edge uv, it cannot, the T minus uv must be disconnected. If it is connected, then there will be another path connecting u and v, which we do not have. So, what will be the number of components once we remove this edge? This is going to be exactly number of components of T, okay, plus 1. So, because the number of components can increase at most 1, and since T is connected, so it is exactly 2. So, you have two connected components of this T minus uv. So, let us call it G1 union G2, and since T has no cycle, so G1 and G2 also have no cycle. So, that means they are trees. So, this is a tree and this is a tree. So, now by induction we can assume that the edges in G1 must be exactly equal to the edges in, so the number of vertices in Gi minus 1. Okay. So, now if you look at the number of edges in G, this is going to be number of edges in G1 plus number of edges in G2, then plus 1 the edge that is which is removed, that uv. So, which is exactly equal to the number of vertices in G1 minus 1 plus the number of vertices in G2 minus 1 plus 1, which is exactly equal to number of vertices in G minus 1, because these two add up to number of vertices in G. So, this proves that the number of edges is exactly number of vertices minus 1 in a tree. Okay. So, we to prove the converse, maybe I will we need some more discussion. I will actually prove it later. But now as an immediate corollary, one can get that every non-trivial tree has to have at least 2 vertices of degree 1. Okay. So, this is an immediate corollary. So, every non-trivial tree has at least 2 vertices of degree 1. Okay. How one can prove this? This is a simple exercise indeed. So, let us start with tree T, okay. So, which is given by V comma E. So, now the T of V is going to be greater than or equal to 1 for all V in V. So, now the handshake lemma says the sum of degree of V in V is going to be exactly twice epsilon, which is exactly twice V minus 1. Okay. So, now since this side is greater than or equal to so number of okay. So, if all of them are actually like all the vertices have degree actually greater than or equal to 2. So, then what will happen? Then this side becomes twice the number of vertices. So, which is going to give us contradiction. So, that tells immediately that this cannot happen. So, that tells immediately that there are 2 vertices at least that should have degree 1, okay, because this entire sum is equal to 2V minus 2. Okay. So, maybe the way we can do this, we write it like this: summation dV V in V is exactly 2V minus 2, and since this is greater than or equal to V. So, if we actually kind of rewrite maybe this summation as sum of 2 things. So, sigma 1 plus sigma 2, where sigma 1 is having all the vertices of degree 1 and then sigma 2 having all the vertices that has degree at least 2. So, then what will happen to this cardinality of sigma 1 will be plus the number of vertices, okay, which is V minus the cardinality of sigma 1. Okay. Okay. So, it is not very hard to see actually, because the sum of the degree is exactly twice V minus 2. So, since all the degrees are greater than or equal to 1, you can easily convince yourself that at least 2 vertices will have degree 1. Maybe we do not need further explanation. Okay. So, now let us actually get into this another characterization using cut edge, which is much more interesting. So, we call some edge cut edge. When we remove that edge from the graph, then the number of connected components should increase. So, an edge E in E is called a cut edge if omega of g minus E is greater than omega of g. Okay, that should be the case. So, now what one can prove, it is a very interesting theorem about characterization of cut edge, and edge E of g is a cut edge if and only if, so E must be contained in no cycle of g. So, E is contained in no cycle of g. Okay. So, this is actually like something one can just imagine. It is not a big difficult problem to see. So, because when we are actually removing this edge, so then it is going to give actually 2 connected components. Okay. So, but if it is part of actually some cycle, so then by removing this edge, we are not going to get 2 different connected components. We are going to just have like we will not produce any new connected components, we will stay as connected. Okay, so that is the basic idea behind this cuttage. So, cuttage means whenever you remove it, you should produce new connected components. If it is part of cycle, then definitely you can't produce new connected component. Okay, so this pictorial proof tells you already how to prove this. So, maybe I will leave it to you to write rigorous proof for this fact. So, now using this one can give the characterization of tree in terms of cuttages. So, you can prove that a connected graph is a tree if and only if every edge must be a cuttage. Okay, here is the theorem. So, a connected graph is a tree if and only if every edge that you take in the graph is a cuttage. Okay, so how do we prove this? You start with the tree and then look at E be an edge inside inside this tree. So, since G is let us say okay, G is your tree, this G is acyclic, that means it does not contain any cycle. So, E cannot be contained in any cycle of G. So, that implies E is not contained in any cycle of G, because G itself does not have any cycle. So, E cannot be contained in any cycle of G. So, that would imply from previous observation E is a cuttage. So, now if you assume that all your edges are cuttages, so then G must be connected, otherwise what will happen? If it is not connected, then it must contain a cycle. Okay, if G is not a tree, okay, then that would imply that G has a cycle. So, if you take any edge inside the cycle, so that cannot be a cuttage by the observation about cuttages. So, that tells you that G must be a tree. Okay, it is an easy characterization that tells you that when tree can be when the connected graph can be tree. Okay, now using this one can immediately see that every connected graph must contain a spanning tree. What is spanning tree? Spanning tree is a subgraph of G, which is spanning subgraph that itself is a tree. Okay, for example, if I take some graph like this, then if I focus only on this part, so then this is indeed a spanning tree inside the graph. So, spanning tree is nothing but a spanning subgraph that itself is a tree. So, and every connected graph must contain a spanning tree. Why? Because you start with the connected graph G. Okay. So, then what we can do? We can actually pick edges which are not cuttages, then we can start removing them. Okay. If G is tree, then there is nothing to prove. Okay. If G is not a tree, so then G must contain a cycle and then you pick an edge inside G and then remove it, then still it is connected. So, then we continue this process until we reach actually all the edges are cuttages. So, then by previous characterization, then we reach a tree. Okay. And in this process we are not removing any vertices. So, that tells you that whatever the resulting graph which is a tree that we get is nothing but spanning tree. So, this also implies that if G is connected, So, then that would imply that the number of edges in G must be at least number of vertices minus 1, because if G is connected, then by deleting non-cut edges we reach all edges being cut edges. So, that means we reach spanning tree. For spanning tree we have this property. So, now if T is a subgraph of G which is a spanning tree, then the number of edges in G is greater than or equal to number of edges in T, which is greater than or equal to number of vertices in which is equal to number of vertices in T and then minus 1, but which is same as number of vertices in G minus 1. Okay, that proves that number of edges must be at least number of vertices minus 1. So, these are all some basic facts about connected graphs, okay, which are important. Okay, so let me actually talk about this Euler tours, okay, and Hamiltonian cycles. So, what I want to do, like at least I will try to prove like this Eulerian criterion, okay, but I will not prove any of this Hamiltonian criterion and so on, but I will state what they are, so that you will have some understanding about them. So, to talk about Eulerian, we need to first define what is Euler trial and Euler tour and so on. So, let us actually start with that. So, we want to talk about Euler trial and tour. Okay, so a trial that actually traverses every edge of G is called an Euler trial of G. So, we have to kind of go through all possible edges of G. Okay. So, such a trial is called Euler trial. So, let me just state it properly. Euler trial, it is a trial so note that in a given trial all the edges must be distinct. So, in this trial we go through traverses every edge of G. Okay. So, indeed Euler was the first one who investigated the existence of such trials in graphs related to, as I said, in this Königsberg bridge problem. Okay, that is why we call this trial as Euler trial. Okay, what is Euler tour? It is a tour of G, first of all, is a closed walk that traverses each edge of G at least once. So, a tour of G, it is a closed walk that traverses each edge of G at least once. So, you just go through each and every edge at least once. So, that you call it as tour. What is Euler tour? An Euler tour is a tour which traverses each edge exactly once. So, in other words, it is a closed Euler trial. So, what is Euler tour? So, it is indeed a closed Euler trial. So, you take a closed walk that traverses each edge exactly once. So, you take a closed walk that traverses each edge exactly once. Okay, that is what you call it as Euler tour. A graph is called Eulerian if it contains an Euler tool. Okay. So, a graph is Eulerian if it contains an Euler tool. So, now what we are interested in actually characterizing when a given graph is indeed Eulerian. Okay. So, let me state this result. So, here is the theorem: a non-empty connected graph is Eulerian if and only if it has no vertices of odd degree, no vertices of odd degree. Okay. So, it is a very nice characterization. So, in particularly like you can look at this Königsberg this bridge problem. So, if you recall the graph of that looks like this. You have these 4 vertices which are representing the lands, and then the edges are the bridges between them. So, you have this A, C, B, D. So, and then you have bridge between AC and AD. Similarly, you have 2 bridge between C and B and 2 bridge between D and B. And clearly, the degree of A, C, D, they are all like not only that, all of them are odd. So, it violates the condition in the theorem. Okay. So, then this is not Eulerian. So, not Eulerian. So, the problem is actually so indeed Euler showed that it was impossible to cross each of the 7 bridges of Königsberg once and only once during a walk through the town. Okay. So, we are looking for Euler trial actually in this graph. So, Euler tour is actually a bit stronger, but anyway even we will see that even this Euler trial is also not possible here, okay, because this violates so much. Okay. So, I will actually stop here. So, we will actually continue with the proof of this in the next class. So, then later like I said we will actually talk about Hamiltonian cycles and so on. I will stop here. Thanks.